All right, boys and girls, welcome back to the drive-thru. Sponsored as always by the deli. Hungry? Stop by the deli. Get yourself some ribs. All right, we're doing number 82 and 84 from section 11.1. Okay, both of these are like getting at the concept questions, so they're smart questions to ask because often the best of these questions show up on quizzes and tests. So it says if r of t is a vector-valued function, is the graph of the vector-valued function u of t, which is represented by r of t minus 2, is that just a horizontal translation of the graph? Well, the short answer is no. Okay? But let me make sure you understand that so to demonstrate this, let's consider our popular little double helix, or single helix in this case we'll just do. Okay, so let's consider the function r of t is equal to cosine theta sine theta, or sorry, cosine t sine t comma t. Okay, and then u of t then is cosine of t minus 2 sine of t minus 2 and then t minus 2. Okay? And for this case, I think it illustrates it better for me to use degrees. So if let's just pick 0, 90, 180, and 270. Okay, so cosine, these will be easy, and the next one will be a pain. Cosine of 0 is 1, 0, 0. Then we've got 0, 1, 90. And then we've got negative 1, 0, 180. And then we've got 0, negative 1, 270. So let me graph that half helix. It starts here. And then it goes up here. So that's 90. Then it's going to be in the back. Up here. Then it's going to be over here. So it looks like that. Okay, now, if you think about this is going to be the cosine of negative 2 degrees, which is really close to 0. I'm sorry, really close to 1. It's 0.9994. Okay. The sine of 2 degrees, sorry, of negative 2 degrees, is negative 0.034, and then this will be a negative 2 here. So, let's see. That means it's going to be like right here. Okay, well, what I want you to envision is that's just t equals 2 seconds ago. 2 seconds ago. So if we would have kept this going like this, that's 2 seconds prior to that, 2 degrees prior to that. That's where it would have been. And then that's how all these are going to be. The next blue point is going to be right here, 2 degrees prior to that black point. So we're now thinking of t in terms of time as the graph is traced out, but you should also just think of it as it's the function 2 degrees ago. So the graph of r of t is going to look exactly the same as the graph of u of t once you trace it out, because we can put in infinitely many values of t and make sure that we have our orientation properly labeled. Okay? No boom yet. 84. 84 is going to be a little quicker. Uh-oh. Maybe not. Paul's feature. Okay. State the definition of continuity of a vector-valued function. Well, I will read that from page 790 in your book. A vector-valued function R is continuous at the point given by t equals a if the limit of R of t exists as t approaches a, and if the limit as t approaches a of R of t equals R of a. Well, so give an example of a vector-valued function that is defined but not continuous at t equals 2. Well, what if R of t was a piecewise function? That's the exception to the rule. So if R of t was 3i as for t less than 2, and R of t was negative 2j for t greater than or equal to 2. Okay, it's oh gosh, I can just make that I. Okay, well, here, let's see, the function is continuous, but since the limit as x approaches t from the left is different than the limit as x approaches t from the right, then this is not a continuous function at t equals 2, even though it is defined at t equals 2. And that would be your counterexample. 84 will not be on the test. 82 will. Boom!